Hello there. The topic of my presentation is mechanical behavior of rock materials with reference to weathering rates. So in this lecture, I will essentially focus on my research experience with reference to the stated theme. So this is the outline of my talk. So I'll talk about weathering and weathering classifications, which should be followed by identification of the problems. Then I'll speak on mechanical behavior of granitic and quartzitic materials with regard to weathering rates. This would be followed by shear behavior of quartzitic joints with reference to weathering rates of joint surface materials. And then I'll be talking about a modified JRC-JCS model and its applicability to weathered rock joints. And finally, I'll mention the salient findings. Weathering is the decay of rocks by biological, chemical, and mechanical agents with little or no transport. Now, when we talk about weathering, this involves three different processes. One is physical weathering, one is chemical weathering, and the other is biological weathering. Now, the biological weathering process can be split or can be categorized into physical and chemical weathering components. So basically, we have two different weathering processes. One is physical weathering process and the other is chemical weathering process. So if it is a purely physical weathering process, it involves processes like thermal expansion and contraction, wetting and drying, freezing and thawing. So all these things are involved in physical weathering process, and when it is purely a physical weathering process, we can expect disintegration of the rock materials without any chemical change or any chemical alteration of the constituent minerals of the rocks. Whereas if it is chemical weathering, it involves alteration of mineral constituents of rocks. And there are several processes that are involved in chemical weathering. For example, you have solution, you have hydration, you have oxidation reduction, you have carbonation, you have hydrolysis, which is very, very important. And because of that, we get the altered minerals when you look at the weathered rocks. Just for an example, feldspar gets altered to some clay minerals. Now, when we talk about these two weathering processes, it does not mean then that they are the standalone processes. Okay, they go hand in hand most of the time, unless it is a very, very extreme climate. Now, when we are talking about this physical weathering process, in terms of manifestation of this physical weathering process, we can get different fractures, which are actually because of the release of locked-in stresses. It could be thermal stresses, it could be removal of confinement, etc. Now, when we are talking about chemical weathering processes, as I have said, this relates to the changes of the existing minerals of the rocks, right? So that is the alteration of the existing minerals. Now, when there is a physical weathering, of course, new surfaces are created which can actually accelerate the chemical weathering process as well. So therefore, and the vice versa, for example, if there is chemical processes, because of which minerals are altered, and it can also induce some of the physical weathering processes as well. So here are some examples of weather profiles from India. For example, we can see here a weather profile, a good outcrop of Singhum granite, Manajkhan granite, and quartzite from the Chai Basa formation. We also have here some weathered granitic materials which are from Hong Kong. So this is just to show you how the weathered rock materials look like in the field, and also when the drill cores are retrieved. So this is a very general schematic diagram of a weathering profile. That means how a weathering profile should look like. So there were several models that were proposed. However, the third one here that we see proposed by Shaw is probably the most acceptable schematic diagram of a generalized weathering profile. Now here we can see that the weathering front is appearing as at different depths, or in other words, the bedrocks are appearing at different depths, although the two locations are not very far with respect to each other. And these kind of profiles are very common, which are essentially controlled by the existence of major discontinuities like faults, some master joints, etc. And not only that, the discontinuities are also responsible for giving rise to some core stones, as we see it here. Adjacent to that, we can find some relic joint stresses. Okay, so actually core stones are essentially the rock boulders which are surrounded by more weathered profiles, as we can see it here. So this is the most acceptable generalized weathering profile that is normally found in tropical, subtropical areas. Now coming to the weathering classification, so we essentially have two different classifications. One is for rock materials, that is for uniform intact piece of rocks, and the other is the rock mass. Okay, both are six-fold classifications. In the rock materials, we call them weathering grades. That is from weathering grade 1 to weathering grade 6, out of which grade 1 to grade 4 are essentially rock materials, whereas grades 5 and 6 represent soil materials. When we talk about weathered rock mass, we call them weathered zone. So instead of grade, we call it here weathering zone. So it is also from grade 1 to grade zone 1 to zone 6. But the thing is, the difference is, unless we characterize the weathering grades of the materials, we are unable to characterize the weathering zones of the rock masses. As you can see it here, when it is weathering zone, it is 100% materials which are grading from 1 to 3. Okay, so it means the first and foremost thing for a practitioner is to identify or categorize the weathering grades of the concerned materials. When we look at this weathering classification, that is this common six-fold classification, it should be remembered that this particular classification is purely based on chemical weathering processes, or it is based on the manifestation of chemical weathering processes. Okay, it does not specifically take care of the manifestations of physical weathering processes, and therefore this gradational thing is possible to be captured through this classification system. As you can see it here, from trace to residual soil. So from trace, slightly weathered, moderately weathered, and highly weathered, up to this it is rock material, and beyond that completely weathered and residual soil, which are essentially belonging to the soil material categories. Now this particular classification is applicable to most of the rock materials, as suggested by Anon 1995. However, this particular classification is not applicable for carbonate rocks, although carbonate rocks undergo chemical weathering only. The reason being, in case of carbonate rocks, when the rock gets weathered, it goes into solution, keeping behind the material which is nothing but carbonate. So the radiational change is not possible to be captured with the help of this six-fold classification system. However, other rock types is possible to be categorized in terms of weathering grades. So we'll be coming across several such examples. One more thing, when we look at this six-fold classification system, since it is based on subjective criteria, it is always confusing to categorize a particular grade, and particularly to confuse between two adjacent grades. For example, whether this particular rock belongs to grade 2 or grade 3. It is grade 3 or grade 4. So these kind of confusions are always there, but sometimes at some grade boundaries there are some specific ways to discriminate the adjacent weathering grades. For example, we can discriminate grade 4 and grade 5 materials just by immersing a piece of rock lumps into water. So if it is grade 5 material, which is actually belonging to a soil kind, it will be disintegrated immediately. But if it is a grade 4 material, and when it is immersed into water, it will remain there for some time. It will not be disintegrated as soon as it is immersed into water. So this is a very quick test to discriminate between grade 5 and grade 4 materials. Although they look very similar here, you see, because it is grade 5 and grade 4 materials of granitic rocks. They look quite similar. However, this little test can help us discriminate the weathering grades very quickly. However, we are not so lucky for other adjacent grades, and therefore we have to depend on some quantitative measurements. It cannot be solely based on the subjective criteria as it is there on the table of six-fold classification. But we have to remember the first thing to discriminate the weathering grades or to categorize the weathering grades is to follow the six-fold classification scheme. And then we can refine that classification with the help of some quantification methods, like with the help of some index tests. So, if we state the definition of the problem, we can state it like this: the ongoing process of weathering in nature produces progressive but intricate changes in rock microstructure at shallow depths where most engineering works are confined, especially in tropical and subtropical areas. Evaluating mechanical behavior of rock materials with reference to weathering grades is therefore important for an engineering work encountering decomposed rocks. There is a number of studies that have been carried out by several researchers in this regard, and here are some examples to name a few. However, assigning weathering grades to rock materials has always remained a challenging task. So first, I'll talk about mechanical behavior of granitic and quartzitic materials with regard to weathering grades. I investigated Hong Kong granite during my PhD study, and this is the geological map of Hong Kong. The core samples from these three sites were investigated. This is the distribution of ground and bedrock surfaces at these three different sites, and as it depicts the variation of bedrock appearance or the variation of the depth of the bedrock appearance is quite different at 3 different sites, which is dominantly controlled by the different discontinuities. This particular picture shows the rock cores and the corresponding photomicrographs, and as you can see, the weathering grades were assigned to this rock cores, and it is to note that no soil material was investigated, and therefore the weathering grade considered or weathering grade that could be assigned to the materials were from grade 1 to grade 4. It is as per the 6-4 classifications. However, depending on the appearance and characteristics of the rock cores, there were 2 intermediate grades that were introduced, that is grade 1 to 2 and grade 3 to 4. The corresponding photomicrographs shows how the deterioration of the material is taking place. First, this particular column shows the general view of the thin sections. The second column is focusing on the changes of the biotite grain as the weathering grade intensifies, or as the weathering intensifies. The biotite is becoming more and more chloritized, as you can see it here. And when the grade is very high, only biotite grain skeletons are present. If we look at the quartz grains of course do not get altered to other minerals. However, it gets more and more disintegrated as weathering intensifies. In case of feldspars, they are getting more and more sensitized as weathering grade is enhanced. Now the problem is with this kind of categorization or this kind of weathering grade categorization, that this is very subjective in nature, and therefore there should be some quantification methods that should accompany such categorization, and index tests are possibly the best ways to be accompanied with this kind of classification systems. However, in case of index tests, there is a problem of reliability of the test results, because there are several issues that could be scrutinized, and the method should be improved. I'll go one by one about different index tests and the subsequent improvement that we were able to come up with. So first, if we talk about the rebound hammer, it is a very useful tool, and it is a rebound index or rebound value is a very good rock index that could be utilized to categorize the weathering grades. We know that rebound hammer or Smith hammer is a spring-loaded piston, and therefore it is influenced by gravity effect. So if the test direction is not horizontal, the rebound value is erroneous. That means we need to normalize the rebound value in the horizontal direction if the direction of application is not horizontal. And regarding this, we have a chart proposed by Deere and Miller in 1966, where he proposed such a chart where empirically, where this chart was developed empirically, and for 4 different directions, the rebound value can be normalized in the horizontal direction. Now, the issue is, in the field situation, the direction of application of rebound hammer could be anything. So what do we do about it? So therefore, we came up with a theoretical formulation through which the rebound value can be normalized in horizontal direction. And it is, although in this chart, and this is the corresponding chart for the normalization, although this chart is shown for only 4 standard direction of application of rebound values, but
for any direction of application, the rebound value can be normalized in the horizontal direction. So this was an improvement that was done, and subsequently, when the rebound hammer investigation was carried out on Hong Kong granite, it was found that rather than single impact, if we go for multiple impacts, then the difference between the second and the first impact value gives a very good indication of the corresponding weathering rate. And when it comes to N hammer, when we compared N hammer with reference to L hammer, we found that N hammer, because of its high impact energy, provides a even a better indication than the L hammer to categorize the weathering rates. Similarly, when we considered ultrasonic POA velocity, we found that the selection of transducers for ultrasonic velocity measurement is a crucial aspect, and depending on this, there could be a possible error in the velocity values. Because this ultrasonic velocity is dependent on the diameter and frequency of the transducer used. In case of portable common ultrasonic tester, which are also used for rocks as well as for concretes. So we try to investigate this particular technical aspect, and we found that the ultrasonic beam characteristics is very much influenced by this frequency and diameter of the ultrasonic transducer. Okay, so when we say beam characteristics, it is the sensitivity of the beam, it is the beam spread angle, and also it is the near field length. So all these beam characteristics are influenced by the frequency and diameter of the used transducers. So if we have different sets of transducers, which transducer pair we should be using. So in order to solve this, we came up with a theoretical inequation, so which actually says that if we increase the frequency of the transducer to get a better beam sensitivity, the diameter of the transducer also has to be changed following that particular proposed inequation. And in our study, the two transducers that were used, T1 and T2, the frequency and diameter are given here. And here we found that T2, should be giving a better results in categorizing the weathering rates as far as the theoretical formulation is concerned. And when we did investigate with these two transducers, the Hong Kong granite, we saw that T2 is actually gave a better results in categorizing the weathering rates of Hong Kong granites. When we try to use other destructive index tests like point load tests, we found that the point load device normally does not come, I mean, in general use or on shelf, it normally does not come with a distance sensor. However, in the standards, in the rock mechanics standards, it says that when you carry out the point load test, and when you try to calculate the point load strength value, we have to consider the depth of cone penetration. Okay, that means we have to consider the distance between the platens at the moment of failure. And to get this distance between these two platens at the point of failure, we need to have a distance sensor that can give us this distance at the moment of failure. Okay, so therefore, according to the standard specifications, we tried to fit a distance sensor with this point load test system, and we found that when this depth of cone penetration was considered, it gave us a better resolution in terms of categorization of weathering rates, as we can see it here. Okay, so this IS50 final is the point load strength index when the depth of cone penetration was considered. So it is giving a better result than the situation when this depth of cone penetration is not used. When we try to use this Brazilian test, although it is very common nowadays, and it is much more common than direct tensile test, it is still an index test. We cannot call it a direct test like uniaxial tensile test or something like that. It is always an indirect tensile strength test. So when we actually carried out this test, we try to investigate the deformation that is taking place orthogonal to the loaded diameter. So what we did, we actually pasted the strain gauges, which is parallel to the horizontal direction and orthogonal to the loading direction, and we tried to find out the induced tensile stress, which is coming from the tensile strength formula of Brazilian test, and the corresponding tensile strain, that is the strain perpendicular to the loading direction with the help of that strain gauge. And this is how the stress strain graphs look like. And here it was found that when the initial at the initial stage of loading, if we consider the tangent modulus, okay, we named it as Brazilian deformation index. We found that Brazilian deformation index is much more efficient than the Brazilian tensile strength in terms of categorizing weathering rates. Okay, so these were some of the improvements that we could we were able to do as far as the investigation of Hong Kong granite is concerned, and as far as the categorization of weathering grades are concerned. And this particular thing, this particular diagram, the third diagram is the stress strain diagram under uniaxial compression test, and we can see as the weathering grade intensifies, how the nature of the stress strain curve is changing. Okay, so the plasticity is increasing, as you can see, and the strength and Young's modulus is decreasing as weathering is intensifying. So the thing is, the improvement of the different improvements of different index tests not only helped us categorize the weathering rates in a more efficient way, but also they were better related with the direct mechanical properties like Young's modulus, like uniaxial compressive strength. So the relevant articles in this regard are enlisted here. So if anybody is interested, can look at these articles. Next, I'll be talking about the investigation of E2 granite. So this is a granite which is from the southeastern Brazil, and this is a part of my postdoctoral research which I pursued in University of Sao Paulo. So this is the site location, and this is the categorization of weathering grades following the six-fold weathering classification. And as I said before, also in my investigation, all the rock materials were investigated, soil material was not considered. So therefore, the weathering grade is confined between 1 and grade 4. Okay, so beyond grade 4, no material was investigated. However, in case of E2 granite, we could found an intermediate grade, which is grade 2 and 3. So if we just want to compare this categorization with the categorization of weathering grades of Hong Kong granite, we can see that even if both are granitic rocks, from place to place, depending on the type of granite and depending on the geology of the granite and the subsequent history, geological history, we can get different weathering grades, that is in terms of intermediate grades. Okay. However, whenever we try to differentiate the weathering grade or discriminate the weathering grades or assign the weathering grades, we have to primarily follow the six-fold weathering classification that we discussed before. So, these are on the left-hand side. I show you the photomicrographs corresponding to this E2 granite with reference to different weathering grades. And some of the things which are similar in this case also, the biotite is getting more and more chloritized, the feldspar is getting more and more sericitized, quad is getting more and more disintegrated. So these things are pretty common in both granitic rocks. In this case, when we used rebound hammer, that is the both hammer, air hammer and in hammer, and we tried to apply this multiple hammer impact on the granitic materials. It was also very clear that the difference between the second and first rebound value gives a very good indication of the weathering grade. As you can see, when it comes to grade 4, of course, no rebound value was obtained because the material was so soft that we could not get the subsequent rebound value. Okay, the first rebound value could be obtained, which is shown here in the table also, but the second rebound value could not be obtained as the material fails by that time. Okay, so next, I show you the stress strain curves under initial completion test. So the pattern of the curves, the stress strain curves with reference to weathering grade is somewhat similar as we saw it in case of Hong Kong granite rock also. But the thing is, of course, the absolute values of the mechanical properties like strength, like Young's modulus, they are of course different in case of E2 granite. And as the weathering grade intensifies, although the strength and Young's modulus get deteriorated, the Poisson's ratio keeps on increasing, which is also expected actually. Okay, which is expected from the nature of the curve. And then when modulus ratio was plotted with reference to UCS, we got the distribution of this modulus ratio along this with reference to these two lines like this. So it is pretty close to the boundary line which is indicated by 500 to 1. Okay, so that is in terms of modulus, the distribution of the data with reference to modulus ratio as far as the E2 granite is concerned. Okay, so now I'll be talking about quartzite rock or quartzitic rocks from India, so which is essentially from Chaivasa formation. So this is the site location, and that is how the exposure or the outcrop looks like. And these are the kind of materials that we found in the site. So this was very interesting to investigate, because quartzite essentially is as good as monomineralic rock, I could say. Of course, it is not monomineralic, but the percentage of quartz could be as high as 90 to 95% or even more. So even in that case, if it is predominantly quartz dominated, how we get the different categorization appearances through which we can discriminate the weathering grades. So that is actually well, that was really interesting to note. So essentially, the minerals which are present in minor quantities, like biotites and some other oxides, they actually give the different appearances of quartzitic materials as weathering grade intensifies. So which is pretty clear from this particular table. So these are the macroscopic pictures, and these are the characteristics, and as we can see, with the help of these characteristics, which is in compliance with the six-fold weathering classifications that we talked about before, the weathering grades of quartzite rock materials can be can be discriminated very well. Okay, so that is weathering grade 1 to weathering grade 4. Now, in terms of photomicrographs, as you can see, when it is grade 1, the quartz grain boundaries are quite intact, but in case of grade 4, it is very loose, and the fluidization of biotite is also there at as in the weathering intensifies. In case of grade 4, the discoloration, or in terms of the color that we observe in case of quartzitic rock is absolutely remarkable, and it is very discriminating with reference to the other grades. So even the quartzitic materials were possible to be categorized in terms of weathering grades following the common six-fold classification. However, it was not enough, and we also carried out other index tests as we did before also for other rock types. For example, in this case, the L-hammer rebound value ranges are given over here, so which gives quite a good resemblance as far as the categorization of weathering grade is concerned. And when we try to find out the Brazilian tensile strength with reference to weathering grade, we found that at the onset of weathering, or at the initial stage of weathering, the tensile strength drop is very sharp, compared to the subsequent stages. Okay, so this is something very interesting to note. And so when we compared different mechanical properties of two different granitic rocks, like Hong Kong granite and granite from southeastern Brazil, and also of quartzitic materials from India. So these are the kind of mechanical property ranges that we could find. Okay, so this is a summary sheet you can see. One thing is very prominent from this summary sheet. When we look at the mechanical behaviors of particularly the direct mechanical properties of different rocks with reference to weathering grades, we can see that at the first stage, or at the initial stage of weathering, the absolute drop of mechanical properties is sharper than it is at the subsequent stages. So this is probably related to the dependence of microcracks of the mechanical properties at the initial stage. When the weathering intensifies, the distribution of these microcracks becomes so abundant that it is hardly any more dependent on specific microcracks, which would be controlling the failure behavior. So at the initial stage or at the onset of weathering, the absolute drop is much more significant than at the subsequent stages. But of course, the mechanical properties are getting deteriorated, but the fall is less severe than what is at the initial stage of weathering. Next, I'll talk about shear behavior of quartzitic joints with reference to weathering rates of joint surface materials. The objective of this study is to understand the influence of weathering on the shear behavior of rock joints. In order to do that, we need to eliminate the influence of other parameters like JRC on shear behavior. So there are two ways to deal with this problem. One is to collect rock blocks from the field and go for shock cutting and then perform direct shear test on the shock cut surfaces. But this is far from reality because these are not real natural rock joints. The other option is to collect jointed rock blocks and check their JRCs in the laboratory and ascertain the JRC equivalence. So the next option was preferred, and we collected jointed rock blocks where the joints were free from any infilling material. They were unfilled joints. To investigate these quartzitic joints, we had another advantage that in case of quartzitic joints, the influence of mineralogy will also be minimum, as quartzite is primarily composed of quartz minerals. So this is the outcrop from where the jointed block samples were collected. Multi-stage direct shear tests were performed at low normal stresses at 3 different subsequent stages, and this low normal stress is in compliance with the shallow depth where this weathering is primarily expected. As we investigate joint surfaces composed of grade 4 surface materials, we could not go for subsequent stages of shearing. We could only perform one shear test on these grade 4 surfaces, and the reason being the specimen gets fractured after one test itself. So when we analyze the data, we found that the shear strength, the peak shear strength, gets deteriorated as weathering intensifies. We also, found out the peak friction angle, and we also found that peak friction angle also shows a negative relation as the weathering rate intensifies. Now, this is a very, very interesting plot. It shows that the difference of peak shear strength at different weathering grades gets intensified at higher normal stresses. So it means the implication of this particular observation is the minor asperities which are present, because planar joint surfaces were considered, the JRCs were equivalent that I already mentioned, and the JRCs were less than 5. So for minor asperities, as far as the JRCs are concerned, controlled the strength of the asperities. Okay, so this minor asperities actually controlled the strength of the asperities, which in turn controls the shear behavior of rock joints. So this is a very, very interesting observation. Next, I'll be talking about a modified JRC-JCS model and its applicability to weathered rock joints. I'll be brief in my description. So it is not that shear behavior of quartzitic rock joints were investigated with reference to weathering rates, but also granitic rock joints investigated with regard to weathering rates. And when more than 100 data were compiled from different directional tests, and when they were plotted in compliance with the three variables like tau p by sigma n, JCS by sigma n, and JRC, we found a modified JRC JCS model, which is given over here. So it has been published in Bulletin of Engineering, Geology and the Environment very recently. So one can take a look at this particular criterion, and we also cross-checked the validity or the efficacy of this particular shear strength criterion with reference to other very popular shear strength criteria and very efficient shear strength criteria like Barton's criteria and other similar criteria. And this new model that is presented over here proves to be more effective or more efficient than the other related criteria. So in one sense, it is simple because it is JRC-JCS model, and on the other hand, it gives or it proves to be more efficient than other similar criteria. Later on, although it is not there in this particular paper, later on we cross-checked its validity with reference to even carbonate joints, where we normally do not see any gradational change, but with laboratory simulation of acidic environment, we investigated the joint surfaces of limestone, and we found that this particular JRC-JCS model performs efficiently in case of those limestone joints as well. So it really looks to be very, very promising. And in this case, with reference to weathering rates, what we need to do, we simply need to find out the determine or assign the weathering rate of the surface material of a joint surface. Then we need to depend on JCS, which could be indirectly found through these rebound hammer values and related dry density, through Deer and Miller equations, and then we can find out the JRCs, and we can find out if we know the normal stress at which we want to find out the peak shear strength, we can find out very easily. So it is a very, very easy method, and it seems to be, and it has been already proved to be more efficient than some other related parameters, and it looks very, very promising. But of course, further investigation needs to be done, in different in other rock types also. But we already have checked it with various, very different rock types with various weathering rates of joint surfaces. So coming to the salient conclusions. The conventional six-fold weathering classification for uniform materials is as capable of capturing gradational weathering induced changes of quartzitic materials as it is for polymineralic crystalline rocks like granite. Use of different indices determined by improved test methods can refine the weathering rate categorization of rock materials. Moreover, improved index tests can help estimate the mechanical properties of rocks more reliably. The highest degree of sensitivity of UCS, Young's modulus, and Brazilian tensile strength of both granite and quartzite at the early stage of weathering can be attributed to sudden augmentation of microcracks and flaws of these materials with the onset of weathering. The difference of peak shear strength with reference to weathering grids becomes prominent in case of shearing stages at comparatively higher normal stresses. In case of planar joints with fine asperities, as investigated in this study, degree of weathering that influences the rock strength plays a key role to determine the resistance to shearing, and this influence becomes prominent at high normal stresses. The modified JRC-JCS model proposed by Ram and Basu 2019 that has been published in Bulletin of Engineering, Geology and the Environment looks to be promising in estimating peak shear strength of natural rock discontinuities across the weathering spectrum. However, further investigation is required in this regard. So these are the references that are cited in this particular presentation. I acknowledge all my co-authors. So I show you a picture of my institute, that is Indian Institute of Technology, Kharagpur. So that is the main building of my institute. And at the end, I thank you for your attention, and I wish you a very happy and safe New Year 2021. Thank you.